Okay, welcome to an extremely quick introduction to differential equations. So first, what's a differential equation? That's an equation that has derivatives in it. How about the order of a differential equation? That's the order of the highest order derivative in the equation. A couple examples real quick. This is a differential equation because it involves derivatives. What's its order? It has the highest derivative is a first derivative, so the order is 1. Here's another example. That's a differential equation because it involves the derivative of a function f. It looks like a second derivative, so the order is 2. What's a solution to a differential equation? This takes a little bit of an adjustment compared to what you're used to with algebraic equations. A solution to a differential equation is a function satisfying the equation. A quick example. Show that y equals 5e to the 1/2 x squared is a solution of y prime equals xy. So to demonstrate that something is a solution to a differential equation, you just run it through the equation. I'm going to differentiate it. Right? Differentiate with respect to 1/2 x squared. Then the chain rule says tack on a derivative of 1/2 x squared with respect to x, which is 1/2 times 2x. The 2's cancel. And what I end up with is an x times 5e to the 1/2 x squared. But that's what y was, so I have xy. So we verified that this function here solves this differential equation here. Next, solutions to differential equations come with flexibility. A first order equation comes with one arbitrary constant. A second order equation comes with 2 arbitrary constants, and so on. So for example, show that y equals x cubed over 3 plus some arbitrary constant is a solution to this first order differential equation, y prime equals x squared. So to get this done, we would take the derivative of it. The derivative of y prime, well, the c disappears. Bring down the 3 out in front. And I end up with x squared. So I have infinitely many different functions that solve this differential equation, just depending on what I choose for that constant c. So this infinity of different curves that solve the differential equation is called a family of curves. And I'll just pop that into the picture real quick for the previous example. So there's my family of curves for several different values of the constant c. All right, finally, we can nail down which particular curve we want to talk about as the solution to the differential equation by specifying an additional requirement called an initial condition. For example, we just verified a general solution to a differential equation. If we added to that an initial condition, so an initial requirement that y of 0 is equal to 1, it would specify what c is, and we get what's called a particular solution to the equation. So I just plug in y of 0 is 1. So y is 1 when x is 0. And it turns out that c must be equal to 1. In other words, the particular solution to the differential equation is found by replacing c with 1. Now I could replot my family of curves with that particular solution highlighted. And there it is. That's our extremely quick introduction to differential equations.